All right, guys, so in this video, we are going to be talking about trends and characteristics of function values that we see on the y-axis. And we're going to start by talking about extrema. Now, we're going to say that extrema are the maxes and the mins of function values. We know that function values are the y values of the function. So really, we're talking about the greatest and least y values that a function attains. When we talk about an absolute max, we're talking about the greatest y value or function value that a function attains. If we look at our graph to the right here and assume that our function is going down to negative infinity on both sides, we can say that we have an absolute max at this ordered pair right here, because that is where we are getting the highest. So we have the highest function value on the graph of our function. Now, when we're talking about local maxes, we're really talking about greatest function values within an interval on the x-axis. So if I can frame a function value within an interval where it is the greatest function value on that interval, then I can consider it to be a local max. And now right here, if I draw out this interval, I can see that I have a maximum function value at that ordered pair. So I would say that I have a local max there. Now, not every interval is going to contain a local max, but in general what we can say is that if we can draw an interval around a function value, or it has the greatest function value on that interval, then it is a local max. In general, we can say that all maxes are local maxes, and it's only if the local max also happens to be the greatest function value the function achieves that we would call it the absolute max. So when we're talking about mins, we're going to basically be using that same sort of framework for our thinking. In general, we'll say that an absolute min is the least function value a function attains. If we look at our graph to the right and assume that both sides of our function go up to positive infinity, we can say that we have an absolute min at that ordered pair right there, because that is the least function value we're going to attain from the y values in our ordered pairs. Similarly to local maxes, we say that local mins are function values within an interval on the x-axis. So again, what I can say is if I draw this interval out right here, I can see that this ordered pair is going to contain a local min. And again, right here, all mins are local mins, and it's only if the local min also happens to be the least function value that we attain that we could call it the absolute min. In general, graphically, maxes and mins are obviously really easy, because really we're saying maxes are the peaks of the function and mins are sort of the valleys of this. So if we're looking at this graph to our right, I can say that between this local min and this absolute min, I actually have a local max. Now, in general here, I couldn't say that I have an absolute max because the function values go up to positive infinity. So even though this is my only max that I'm seeing, because function values go up to positive infinity, you couldn't say that there's an absolute max. Similarly, with our first graph, between our two maxes, we have a local min, but it couldn't be the absolute min because it's not the least function value we get, because function values go down to negative infinity. Okay, so let's talk about boundedness. Boundedness for functions is really talking about constraints on function values, right? Where basically we're saying function values are not going to do something. If we say that a function is not bounded, though, we're saying there are no constraints. And what that basically means is function values can go up to positive infinity and down to negative infinity. So if we look at our graph right here and say as we leave the graph to the left side, our function keeps going up, we can say that our function values would go all the way up to positive infinity on the y-axis. And as we leave the graph to our right, we could say that if we assume our function keeps going down infinitely, we would get all the negative y values on the y-axis going all the way down to negative infinity. And because our function values positive infinity and negative infinity, we'd say that our function is not bounded or unbounded. If our function is bounded above, then function values are kept from going to positive infinity. So if we assume both sides of our function go down to negative infinity, we are not going to achieve positive infinity with our function values because we've got this absolute max right here. And in general, we would say this function would be bounded above. If we're bounded below, our function values are kept from going to negative infinity. So right here with a parabola, we're seeing that vertex as the absolute min, and both arms of the parabola opening up go up to positive infinity. So our function values don't go down to negative infinity, and this function is bounded below. We say a function is just plain bounded if it's bounded above and below. And in general, right here, we're not going to see this from too many functions. The example we're looking at right here is actually the sine wave. And the sine wave is basically a function that oscillates or goes up and down between its absolute max and its absolute min over and over and over again. So it achieves its absolute max with each peak of the wave and its absolute min with each valley of the wave. And in general, right here, since it's just continually oscillating between its max and its min, it never gets to positive infinity, so it's bounded above. It never gets to negative infinity because it's bounded below, so that means that it's just plain bounded. All right, guys, so now we're going to talk about range. And in general, we're going to say that the range is the outputs or the function values for a given function. Now, we know that the function values are the y values of the function, or the y values in the ordered pairs of the function. And in general, when we talk about range, we're going to say that we want to identify a range graphically. So that basically means that when we've got a function like our g of x right here, we're going to type that into our calculator, and we're going to try to identify where we have y values in our ordered pairs by looking at the graph of the function. So we've got the graph of a function to the right here. And in general, what we can say is that we have y values in the ordered pairs of the function where the function runs alongside or covers the y-axis. So right here, because we've got a parabola opening up, I can basically see that I'm covering the y-axis from the vertex all the way up to positive infinity, right? And basically what I'm seeing here is my y values in my ordered pairs are starting at that vertex where I have an absolute min, and they are going all the way up to positive infinity, right? So looking at this guy, basically what I want to do is find the ordered pair of that vertex so I can identify what that absolute min is going to be, and then I'm going to be able to say what exactly my range is. So right here, what we're going to do is take our calculator, and we are going to go to y equals, enter in our function, right? Then we're going to go to graph so that we can see a graph of that function, same graph that we've got on our notes. Now we're going to go to second trace calc. And on this menu, we're seeing both min and max. So this is where we're going to go to find the mins and maxes of our function. So we're looking for the min this time. We're going to press 3, select that min. And what the calculator wants me to do is frame where I want it to find the min on the x-axis. So right here, first it's asking me for the left bound, or the left side of the frame. So I'm going to go to the left of the min and press enter. Next, it's asking me for the right bound, so I'm going to go to the right of that min and press enter. And now I've framed where I wanted to find the min on the x-axis, and right here I'm going to press enter one more time, and it's telling me that I have a min of -3 at the x value of -2. So the ordered pair of that vertex where we have that absolute min is -2, -3. And we are going to go and write that down right here. So we've got -2, -3 as the vertex of our parabola, and we can say that our y values for our function are starting at that absolute min of -3, right? And they're going to go all the way up to positive infinity. So our function values start at -3, and we would say including -3, since -3 is a function value, and they go all the way up to positive infinity on the y-axis. Okay, so right here in general, if we're asked about boundedness, this is a parabola that opens up, so obviously our function values don't go down to negative infinity. We can say here that we are bounded below. If we take a look at our next function, we've got f of x as the linear function 2/3 x minus 1. So of course you'd want to type this into the calculator, and you would see the graph to your right here. So basically what we can see here with this linear function is an increasing function that continues on the slope of 2/3. And basically what we're seeing here is a function that is going to cover the entire y-axis. So basically, as x values go out to positive infinity, our function will continue to increase out this way, covering all of the y-axis, right, up to positive infinity, right? And as x values go out to negative infinity, we'll see our function values continue to go down, basically giving us all of the y values down to negative infinity. So right here we can say the range of this function, or the y values in our ordered pairs, will go from negative infinity to positive infinity on the y-axis. We get every single y value on the y-axis in an ordered pair of this linear function. Since our function values go up to positive infinity and down to negative infinity, we would say that this function is unbounded. All right, guys, so we're going to look at horizontal asymptotes now. We're going to say that horizontal asymptotes are basically flattening out of function values, where we're seeing the y values in our ordered pairs get closer and closer to one y value as the x values in the ordered pairs go out to positive infinity and negative infinity. We're going to be looking at horizontal asymptotes for rational functions, which are basically fraction polynomials, where we have a polynomial in the numerator and a polynomial in the denominator. The first instance where we're going to see a horizontal asymptote for a rational function is if the degree in the numerator is less than the degree in the denominator. Now, remember that the degree is the highest power of the polynomial. We're seeing in our first example the degree in the numerator of 1 for our 3x and the degree in the denominator of 2 for our x squared minus 4. And when we have the degree in the numerator less than the degree in the denominator, we say there is a horizontal asymptote at 0. So right here, for this first example, we're seeing y equals 0 as the horizontal asymptote. Now, if we take a look at the graph of this function, we're basically seeing the y values in the ordered pairs come to the y value of 0 as x values go out to positive infinity and negative infinity. And graphically, it looks like the function is flattening out to the x-axis where y equals 0. Now, the reason we're seeing this flattening out of function values is when we think about plugging in larger and larger x values, the highest powered term in the denominator is growing so much faster than the rest of the terms in the numerator and denominator that it makes the denominator larger and larger in comparison to the numerator, the larger the x values get. So basically what we're seeing here is larger and larger denominators in comparison to the numerator, and that gives us fractions that are closer and closer to 0. So the outputs of the y values are getting closer and closer to 0 as the x values get larger and larger. The next instance where we are going to see a horizontal asymptote from a rational function is if the degree in the numerator is the same as the degree in the denominator. And here we're going to say we have a horizontal asymptote at a ratio of the lead coefficients. So right here, we've got f of x equals 3x squared divided by x squared minus 4. The degree is the same. In the numerator and denominator, we have a degree of 2. Lead coefficients are the coefficients for the highest powered term. So in the numerator, we've got a lead coefficient of 3. In the denominator, we've got a lead coefficient of 1. And right here, we're going to say that we have a horizontal asymptote at the ratio of 3 to 1, or 3. Right? So basically, this function is going to see its function values flatten out to the y value of 3. And if we look at the graph here, we're seeing that flattening out to the y value of 3. As x values go out to positive infinity, as x values go out to negative infinity, we see the y values in the ordered pairs get closer and closer to 3, right? So again, right here, the reason for this has to do with the fact that higher powered terms grow so much faster than terms with lower power. So in general right here, what we're going to say is that highest powered term in the numerator and denominator grows so much faster than the rest of the terms that are in the numerator and denominator, whatever they are, that the rest of the terms only really create a slight difference between the numbers we're seeing in the numerator and denominator with regards to that highest powered term. So really we're seeing, we're getting closer and closer to 3 times a number divided by 1 times a number, right? And basically, as x values get larger and larger, we're getting closer and closer to 3 divided by 1, which gives us y values getting closer and closer to 3. So finally, our last example of a rational function, or the last possibility for a rational function with regards to degree in numerator and denominator, is if the degree in the numerator is larger than the degree in the denominator. And here we would say there is no horizontal asymptote. No horizontal asymptote in this case. The last thing we want to point out is that we can cross a horizontal asymptote. If we look at our first example here, if we plug in the x value of 0, we would get f of 0 as 3 times 0 over 0 squared minus 4, which gives us 0 over negative 4, or 0. And so we're actually seeing the function achieve the ordered pair 0, 0, where the y value is right on that horizontal asymptote. So this is something that we can see for horizontal asymptotes. We don't cross every horizontal asymptote. In our second example, we're not crossing the horizontal asymptote, but it is something that we can see. And we'll look at it again tomorrow in class and come up with a little bit of an explanation as to why we can cross horizontal asymptotes while we will never cross a vertical asymptote for functions. All right, guys, so looking at these problems, I am asking you guys to find the domain, range, and asymptotes for the two functions below. In the direction, I'm asking you to find them graphically and check algebraically. What I want you to do, though, is to go ahead and find the domain and asymptotes algebraically just by looking at the equation, and then check graphically, whereas the range, you're always going to have to find graphically. So you're going to end up having to type in the equation into the calculator and determine the range that way. All right, guys, so pause the video here and we will give these a shot. All right, guys, so looking at this first problem, we're first going to find the domain. And right here we can see our only potential for a domain restriction would be an x value that gives us 0 in the denominator. So we take the denominator and find its zeros, and they are telling us that x cannot equal negative 2 and x cannot equal 2. So right here we get our domain from negative infinity to negative 2, union with negative 2 to 2, union with 2 to positive infinity, where we've excluded those x values. Since the x values giving us 0 in the denominator are not factors of the numerator, we are both going to be vertical asymptotes. So right here we have a vertical asymptote at x equals negative 2 and at x equals 2. We can confirm that graphically. We're seeing the vertical asymptotes on the graph of our function here. And we're also seeing the holes in the domain, where basically we have no function at those vertical asymptotes. Looking right here at our horizontal asymptote, we can see our degree is larger in the denominator for sure. So right here, we have a horizontal asymptote at y equals 0. The range is a little bit trickier, and in general what we want to think here is we are going to want to graphically define where our function is running alongside the y-axis, because that's where we have y values in our ordered pairs. So right here I can say that I have y values in my ordered pairs from negative infinity on the y-axis all the way up to that local max of negative 0.25. And then I don't have y values in this gap right here, but I've got y values after that in ordered pairs, after my horizontal asymptote at 0, all the way up to positive infinity. So right here we would say the range would be negative infinity to negative 2.5, union with 0 to positive infinity, where we're including that negative 0.25 as a function value. Okay, so for our next function, again, our only potential for domain restriction is an x value that will give us 0 in the denominator. So we solve for 0 in the denominator, and we get imaginary numbers. And basically what this means is there is no holes in the domain, because imaginary numbers, I and negative I, do not have any place on the real number line of the x-axis. So right here our domain is negative infinity to positive infinity. We have every single x value in an ordered pair on the x-axis, and we can see that graphically. Also, because those zeros in the denominator are imaginary numbers, we would say that there are no vertical asymptotes. And of course, we're not seeing any vertical asymptotes here either. We can say that we have a horizontal asymptote of y equals 3 by seeing that the degree is the same in the numerator and denominator, and the lead coefficient is 3 in the numerator and 1 in the denominator. So we're seeing our function values flatten out to 3, which we can confirm graphically. And again, with the range here, what we want to do is basically identify where our function runs alongside the y-axis. So we're going to say that we run alongside the y-axis from this absolute min of 0.5 all the way up to that absolute max of 5.5, giving us a range of 5 to 5.5, including both of those function values. All right, guys, so we'll take a look at more of this stuff tomorrow, and we'll